Okay, guys, here's part two of the earthquake lecture. We're going to talk about the different scales that we use to measure earthquakes. And one of them is intensity, and that's a measurement of the amount of shaking. And it's done by something called the modified Mercalli scale. And then the other thing is magnitude. And magnitude is a measurement of the amount of energy released by an earthquake. It's more quantitative. You guys, I think we all grew up with the Richter scale. I think if I told you there was going to be a 7 magnitude on the Richter scale earthquake, you might, be a little bit careful about where you were going to be, preferably, not in a building that's poorly built. And then what I need to tell you about is actually a new scale, a kind of a better scale that we have for really large earthquakes. Okay, and that's called the moment magnitude scale. I've got slides and we'll talk about it. But we're going to start with that modified Mercalli scale. And it's useful because we haven't always had the Richter scale. Dr. Richter, another Caltech seismologist and a Southern California earthquake expert, came up with this in 1935 using the seismograph. And the seismogram measurement. So we'll take a look at that and we'll talk about modified Mercalli. All right, so this is qualitative, okay? Qualitative is descriptive. And so let's say you were cleaning the garage and you came across a letter that your great-great-grandfather had written to your great-great-grandmother, and maybe he was in World War I. And he's describing, his time in Italy and when he felt an earthquake. And he talked about, the shaking and what fell down and what it looked like and what it felt like. You can actually grab that letter and look at, I think it's the next slide, and figure out the number that you would assign on a Mercalli scale to the intensity or the amount of shaking that your grandfather had, your great-great-grandfather had experienced. Now there are some drawbacks. Now you guys, I am not going to ask you for the 12 classes, but just check them out. It's kind of interesting. So this is based on the amount of shaking, and obviously 1 is the lowest and 12 is probably pretty close to what Japan just experienced. All right, problems. I was shaken out of my bed in Santa Barbara by the Northridge quake, but it didn't hurt anything. So I was far from the source, and so there was no damage, okay? But obviously there was a lot of damage in the Northridge quake. All right, the type of rock you live on. Oh boy, this is important. I might have to make another movie about this. If you live on solid bedrock, okay, that's good, especially crystalline type rock. If you live on granite, that's really good. Now, if you live on fill, as many of the people that live in the Bay Area live on fill, it's basically reclaimed swampland. That is the worst thing. And so if you're on bedrock and your neighbor's on fill, your house will shake, but not that badly. Your neighbor's house may be completely destroyed. So that matters. Also, quality of construction. When there's large earthquakes, let's say in Turkey, okay, all the buildings just totally collapse. They have no building code. I mean, they're just barely got a roof over their heads and they can barely feed themselves. And so, it's not really a surprise. Whereas we have a building code here in the United States, and so our quality of construction is a little better. Someplace like Japan has an even better building code than we do. So it just really depends. And then the population. If there's nobody there to experience the earthquake, because they're all too far away, maybe it's a very unpopulated area, then it never happened according to the Mercalli scale. All right, now just a couple of things. Somebody's got to feel it for it to even be a 1. And because I'm pretty comfortable with the Richter scale, I can kind of make some, generalizations about, where this would be. Let me just kind of look. Let's say, how about a magnitude 7? Everybody runs outdoors. Damage negligible in well-designed buildings. Let's see, slight to moderate in well-built ordinary structures. Chimneys broken, noticed by people driving cars. If I had to guess, that's about a 6 on the, or somewhere in the 6s on the Richter scale. Let's go for the worst, 12. Damage is total. Waves are seen on ground surfaces. Lines of sight distorted, objects thrown upwards. Okay, this is probably what they experienced in Japan, and probably even, in some of the other pretty large earthquakes. So, what's that? It just got upgraded to a 9 magnitude. It was 8.9, and it was upgraded because that in Japan was a really, really huge amount of energy that was released. All right, well, let's talk a little bit about magnitude. Now, this is quantitative. This is measured with instruments, okay? Not qualitative, not just saying, oh, it's a nice day. It would be like me saying, oh, it's 70 degrees out. That is a number. That's quantitative, and it's been measured with an instrument. So the magnitude, Richter scale, is based on the seismic record, on that seismogram. When did the first P wave arrive? When did the first S wave arrive? The difference in arrival time, and the amplitude of the largest of those waves, of your body waves. Now, you guys, you understand what wave height or wave amplitude is. Let's go to the beach. We stand in the water and a foot-high wave hits you. You laugh. Okay, now a 20-foot-high wave hits you, you don't laugh. Obviously, a 25-foot or 20-foot wave has a heck of a lot more energy on you. And so if you're standing in front of a seismograph, and there's a little wiggle on it, you might say, wow, I don't even feel the earthquake. But I promise you, if there's a huge wiggle on it, if it's pinning out, you are feeling that. So larger earthquakes have higher amplitudes or wave heights. All right, and magnitude is that measurement of the energy released. All right, again, I was saying it depends on how far or how close you are, and they get that out of the difference in arrival time between the P and S wave, and then also the height of the largest is typically the S wave, the secondary wave. Now, Dr. Richter was from Caltech. That's in Pasadena. He designed it for Southern California earthquakes, where the focus is shallow. Most of the San Andreas fault type earthquakes happen pretty close to the Earth's surface, within a few miles. Okay, underneath a subduction zone, you can have an earthquake happening almost 500 miles deep. Okay, that never happens in California. We don't have an oceanic plate going underneath us. We can't have that type of earthquake. And so, kind of mathematically, it assumes that the depth is 0, and that's kind of what this is. This is not something that we would use for a deep earthquake. It just doesn't work. And this also, I've lived in Southern California for 30 years, and I've been through a ton of earthquakes, but they're all pretty small. Dr. Richter didn't mean his scale to be used by, much more than a 6 or a 6.3 Richter scale magnitude, and I'll show you that. So it doesn't work with deep earthquakes, and it does not work with very large earthquakes. All right, logarithmic means a base 10, and so what that means is that if you're standing in front of the seismograph and there's a magnitude 4 earthquake, you're going to have the squiggles. But if there's a magnitude 5, the squiggles will be 10 times higher. Okay, so they'll just 10 times bigger squiggles. But that's not really what's important. What's important is the energy release, and it's not base 10. Okay, it's exponential in a way. Every time, if we go from a 4 magnitude to a 5 magnitude, 32 times as much energy was released by the 5 than the 4. But let's jump up to a 6, because I think many of us have experienced a 6. It's 32 times 32. Okay, it's not 32 plus 32, 32 times 32, or more than 1,000 times as much energy is released by a 6 than by a 4. And so this is when those big numbers, they just represent, that magnitude 9 just represents a huge amount of energy. It's scary to think of it. All right, now take the red line off mentally. Dr. Richter, this was his scale, and look, he did not mean it to go much above a 6. Now, I can just take a ruler and increase that line, but that line's mathematical, and my line that I draw on there is not mathematical, so it does not work, and Dr. Richter didn't mean it. So what you do is on the left-hand side, you look at the difference in arrival time, and remember, that tells me how far or how close I am, and that's important because if you're far from the earthquake source, you're going to feel it a lot less dangerous, a lot less violent than if you're very close. And what you see is a difference in arrival time of 24 seconds. You go on the left-hand side and you make a little dot on the 24 seconds. And that translates over to, 220 kilometers distance. All right, then you go over onto the right-hand side and you look at the height of the highest amplitude wave in your body waves. And there's your S wave, and you measure it right off that zero line or the quiet line, and it is 23 millimeters. So you put a dot on 23 and hey, you connect the dots. And when you connect those two dots that you made on either side, the line, that red line, goes right through a magnitude 5. Okay, so kind of think about this. This works great for relatively small sized earthquakes. Does not work for very large earthquakes or shallow or deep earthquakes. It does work for shallow. All right, now here's the Richter scale. Again, you guys, you will not be asked to really know this, but if I say there's going to be a 4.0 earthquake, you might not be all that concerned. But boy, if we start getting up in the bigger numbers, you are concerned because you're releasing so much more energy. Now, you guys, look on the right-hand side. We luckily have a lot more smaller earthquakes than larger earthquakes. And like I said, in the past, students always ask me after we have a big earthquake, is this abnormal? And I've always in the past said no. But this year, okay, it's March 2011, I have to actually stop and say, yes, we are having an abnormal year. We are just having some very, very large earthquakes that are just a little bit more. And I don't know what that means. It means that you should probably check your earthquake supply kit, okay? All right, this new scale, and I have seen this published Time magazine, the LA Times. I think your children will grow up with this. It's called moment magnitude. And it's kind of funny. We don't use the seismograph for this. What we use instead are very highly trained geologists. Now, I'm a good geologist, but I'm not trained to do this. These geologists, this takes time, first of all. It's expensive. You only do this with very large energy earthquake. And what you have to do is you actually have to go out and check out the fault zone. Now, the 1906 earthquake, it broke, a huge section of the San Andreas Fault. You could literally drive along the San Andreas Fault. I do this on some of my field trips. And we go to Point Reyes Station, and there's a 17-foot offset, and then we travel kind of down to the Carrizo Plain area, and as we're moving hundreds of miles, the offset gets less and less when we're farther away, and so we could actually still do this for that 1906 quake. Much of that evidence is really, really there by getting on the ground. Now, what the scientists that are on the ground are measuring is the amount of rock that's displaced. So, for instance, it's calculus, you guys. I'm saving you a big calculus formula. At Point Reyes, it's 17 feet. At San Francisco, let's say it was 10 feet or 8 feet. And then the farther you go away from the actual site where the rupture first started, it gets less and less. So you have to. It's a constant that it's changing. It's not a constant. Now you also look, how much broke. The Loma Prieta quake, the World Series quake, it broke a part of that same fault, but a much shorter area. So not as much energy was released than the 1906 earthquake, which broke hundreds of miles along the San Andreas Fault. And then you also have to look at the strength of the rock. And I was kind of hinting at that before. If you're breaking granite, that is a powerful earthquake. If you're just breaking sediments or even weak fractured rocks, so these scientists have to get out on the ground and access all this stuff. And, it's fun to go do this, kind of as a armchair quarterback or something, but they have a serious job to do. And even though they send out independent teams, they pretty much always come back, because they are so highly trained to do this properly with a number. And sometimes that number is bigger than what the estimate using the Richter scale was, and sometimes it's actually smaller. All right, that 1906 quake on the Richter scale would have come out at about an 8.3 magnitude. Now, in 1964, if you guys have been paying attention to the news, they keep talking about Crescent City. In 1964, with no warning, Crescent City got nailed by a big tsunami from that earthquake. It's called the Good Friday earthquake that hit on Good Friday in 1964 in Alaska. And boy, that sounded like a scary earthquake. It shook the ground for more than 4 minutes. Now look at the number. When it was checked out on the ground, Alaska's magnitude went up. So it is just a little bit bigger than that the Japan earthquake that we just had. Okay, but actually San Francisco was downgraded. It could have been worse. And so again, by getting people on the ground, looking how much of the fault broke, how much was the displacement along the entire fault, and what was the strength of the rocks. Okay, it basically, in this case, brought the magnitude for the Alaska earthquake way up and the magnitude for the San Francisco earthquake down. All right, now this we need to update this one. Our publisher hasn't updated this one, but the world's largest earthquake known in recent times is that 1960 Chilean earthquake. And one of my advisors from UC Santa Barbara was there. She was a grad student. Okay, and that was a 9.5. You guys think about it. That the earthquake we just had in Japan, as of right now, is at 9. So this one is the number one in recent time, or in the last 100 years or something that we know of, probably more than 100 years. So the Richter scale, sometimes it underestimates, sometimes it overestimates, but what you'll see is the big changes in the numbers that are above, basically above, too far above 6. Okay, so lots and lots of activity, and if you look at some of these names, most of this activity is on that Pacific Ring of Fire. All right, now this is just kind of mostly conversation, you guys, but this is really important, parts of it, and I'll let you know. What determines how trashed your area is going to be? The intensity of the earthquake obviously matters, the amount of shaking. If there's just a little shaking, not a big deal. If there's a whole lot of shaking and it lasts a whole long time, you are just going to shake down even very strong structures. So that Alaska one, people say up to 6 minutes. Okay, I'm being very conservative with my 3 to 4 minutes. The last earthquake I was in, I think it was 29 seconds, and it felt like 5 minutes. I can't even imagine what that felt like. It must have been just terrible. And these aftershocks that you have, many aftershocks that are really, really big. Now, I'm going to show you guys a great slide about, you care what you build on. If you're going to build your dream house in the Bay Area, you better invest in like a $5 map that shows you the rock type. And you build it on solid rock, okay, consolidated rock. You have a much better chance of living if you are caught at home in an earthquake versus fill or softer sedimentary rocks or sediment. Okay, and then the design of the structure, obviously, and hopefully building codes. You might kind of curse the inspector as they kind of make your life hell as you're building a new structure, but it's there for a reason. And if you live, on a fault and you're a family person, maybe you should even consider building above code because it's going to happen. They call this earthquake in Japan the 1,000-year earthquake, and it wasn't probable that it would happen in your lifetime, but it did, and you never know. All right, where you got to promise me you'll never live, though, is in the Marina District. That is the worst district to live in San Francisco. It is basically filled in bay, and it's loose. You guys, let's say your dog died and you wanted to bury Fido in the backyard. You go in the backyard, you get out a shovel, and you start digging, and the hole fills with water. You can't bury Fido. The water table's very high, the sediments are very loose, so when it shakes, you're going to get what's called liquefaction. It's going to settle, water's going to shoot up in volcanoes of mud and stuff. Now another thing is that, parking is just a bear in San Francisco, so you're like, oh, I must have parking. Well, where's parking going to be? In your base floor. Okay, this is like a house of cards. You're building a house of cards, somebody comes and shakes your table, it's down. And, you don't want, it's called a soft first story. You do not want that. Okay, Marina District, no. The ground shaking, again, that liquefaction. You guys have all heard of quicksand. There's also something called quick clays, and it can just turn, what looks like dry ground into, mud, and water shoots out, and it's pretty trippy. I think I put in a link for a video that shows that. It's that link where it shows the Japan earthquake and the man showing the crack forming. Keep watching it. You're going to see liquefaction. All right, this is where I want to show you guys, and I want to talk about the Loma Prieta quake, or the, what's it called, the World Series quake. And what I want to talk to you guys, again, bedrock is nice solid rock. Alluvium is, sometimes it's sediments laid down by a stream, and then you have an estuary. An estuary is very fine-grained sediments, and then we also have to talk about, human-filled embayments. And, anytime there's, after the 1906 earthquake, they took all that rubble and they filled in parts of the bay, and then they built on it. Not a good idea. So let me just show you, guys can see that last, what I'm going to show you is that when the earthquake wave slows down, the wave height is going to increase. Now this is actual data from the Loma Prieta quake, and what we have on the left is hard solid rock. So if you're sitting in your house on that nice solid bedrock I told you to build on, you get shaken. You know, maybe your favorite coffee cup rolls off and breaks, but you're okay. Okay, now let's go on softer sedimentary rock. Okay, the wave is going to slow down when it goes into this less dense consolidated rock, and wave height is going to increase. This happens at the beach, you guys. You're standing, you're looking like way far out in the ocean, and you're not seeing big waves. What happens is when the wave comes in shallow and it starts to drag on the bottom, the sea floor, when it's really shallow, it starts to build in height because the energy can't move forward, it moves up, and the same thing's happening here. All right, so since it slows down, the height, the wave amplitude increases. All right, well, there's somebody built on coarse grain like gravel, so sediments. And look at what they're feeling. They're feeling something very different. Now, the parts of that 880 freeway that collapsed were on the far right material, silt and clay, fill, unconsolidated sediments. Look at what they experienced. If you lived on the far left type of rock and your neighbor lived on the far right rock, you lost your coffee cup, your neighbor's house might have all collapsed and killed them. So you gotta be aware of what you're doing, okay? It's very, very important. All right, these are those mud volcanoes after the Loma Prieta quake, but I can add in, probably next semester, I'll add in some pictures from the mud volcanoes formed from the violent shaking of the Japan earthquake. Okay, so those were about 10 feet across, and water shot out of there. This, again, if you tried to bury, 6 feet down or something, you'd probably hit water, a very high water table, because you're in low elevation, you're near the ocean or something. All right, the tsunami. Now, in 1946, they developed the Pacific Tsunami Warning Center. And basically, anytime in the Pacific Ring that there is on the proper type of fault, it has to be a vertical offset fault, a magnitude 6.5 or above, you have to have a pretty good sized earthquake to make a tsunami, out goes a warning. Okay, and so they watch. And the reason for this was actually because poor Hawaii, you guys, Hawaii got nailed by, the tsunami from Japan. It's right in the middle of the Pacific Ocean. So if a big earthquake happens in Japan, Hawaii's going to get nailed. In Alaska, Hawaii's going to get nailed. In Chile, Hawaii's going to get nailed. Now, this is what happened basically. We have, the convergent type boundary, the seafloor is being shoved underneath, and it basically pushes up. And when you push up, you displace water. When you displace water, it's got to go somewhere, and it goes into the form of a wave. Now, if you're in the super deep ocean, you may not even know that wave has passed under you, but that wave starts to build in height when it gets into the shallow water, and you can actually watch that happening with some of that footage from the Japan earthquake and tsunami from just this last week. All right. Now here's that poor picture of Honolulu, Hawaii. They get nailed quite often because, look at this. This is the Pacific Ring of Fire. If I could have a red pen, I'd light up pretty much the edges of the Pacific Plate. There are lots of subduction zones, so lots of these type of earthquakes happen. Now luckily, because we have warning, we're a lot better in communication and stuff, there is warning. But you guys, you have to heed the warning. And I think part of what you learned this last week is that sometimes the biggest wave is not the first wave, just because they say, okay, the first wave is supposed to arrive at 8 a.m. Don't run down there at 8:10 to check it out, because the big wave may be the 5th wave or the 4th wave or the 3rd wave or the 10th wave. So you just don't know. In fact, today is Monday. The earthquake happened in Japan on last Thursday night. I just saw the news tonight where they say that the Crescent City harbor is still having surges. The ocean is still sloshing after that. Now, you might look at these times and go, wow, that's, they're slow. No, they're not. They're traveling as fast as a 747. They're traveling 500 to 700 miles an hour. It's just, this is a vast ocean. That's why you have great warning. All right, I believe it's 1942. I can't remember if it's 42 or 46. I wasn't alive. Honolulu got nailed by a tsunami. So this is actually the footage from, the images from that, a wall of water. And this was downtown Honolulu, and it was, people died. It was really terrible, and this is basically what gave rise to this Pacific Warning Center, because we gotta, protect people. Be kind of a good idea. And this is kind of a sad picture. You can see the man that he didn't make it. Okay, and this wall of water coming on. All right. Now, boy, before the Japan event, this 2004 tsunami was even bigger news. And it was really tragic because, you know what? Look at that. It's not the Pacific Ocean. Okay? This is surrounded by non-developed countries. And they didn't have the warning system. People died 10 hours later that should never have died. The warning should have been in. But people in Somalia died. People in Thailand died hours later. Now, this was a huge earthquake. Probably 50,000 people would have died from the earthquake, but over 250,000 people died. That's 200,000 extra people because of the tsunami, and much of that was avoidable. Okay, again, there's kind of, not the best video footage. This is why the event in Japan is so amazing. It's got the best video footage captured of a tsunami event. And this one, right now, it's about rated equal with the, it'll be interesting to see how this works out with Japan. So a moment magnitude of 9. This was pretty huge. It might have gone up to a 9.1. I can't quite remember. If you guys are someplace and there's a big earthquake, go to high ground. If you're at the beach and all of a sudden the water recedes like a super low tide, go to high ground. You can usually hear it. You can see it. Go to high ground. Literally going up in one of those stronger buildings, in this case, just going up to the next floor saved a lot of people. Don't risk your life. Don't risk your loved ones' lives. Avoid this. Educate yourself. Landslides. That 1964 earthquake caused huge landslides in Alaska, and fires. In fact, Japan, they were talking about the last big event that they had. It wasn't even this big as the one we just had. It was 1995, where I think 2,000 people died in Kobe, but the fires were really pretty amazing. So remember, it's not sparking the fire, the earthquake, it's breaking pipes and knocking over lanterns and things like that. Okay. This is that 1964 earthquake in Anchorage. You guys can still go and see this. It's still totally trashed. And this was part of that stuff that those scientists went and walked out and figured out, wow, this was a lot bigger earthquake than we really thought. This is the one that spawned the tsunami that hit Crescent City. Killed people. Okay, so here's just the cartoon that kind of shows you. And this was the quick clays, or the liquefaction. And it's just destroyed. You can't live there anymore. It used to be a beautiful area. All right, again, the 1906 earthquake in San Francisco. All unreinforced buildings collapsed. It was just bad. In fact, they learned a lot about firefighting techniques in a big city and what not to do. But this was a pretty terrible event, and I don't think we'll ever have a true estimate for how many people died. I think it's 2,000 what they're estimating or something, but I think it was probably a lot more.